Riemann sums are a way we can approximate the area under a curve. You're probably wondering, why would I ever need to approximate the area under a curve? Well, imagine you're sitting at home one day and you're really bored and your name happens to be Isaac Newton and you feel like inventing calculus. Well, then you would have to know how to find the area under a curve. Some less common situations would include finding the velocity from an acceleration function or finding the position from a velocity function. A Riemann sum approximates the area under a curve by splitting that area into several rectangles of equal interval. The areas of these rectangles can be calculated to find an approximate value for the area under the curve. To find the exact value of the area under a curve, you would take these intervals of these Riemann sums smaller and smaller until you have an infinite number of rectangles that give you the exact value of the area under the curve. There are three main types of rectangular Riemann sums: left, right, and center. In a left Riemann sum, the height of each interval is determined by the value of the function on the left side of the interval. In the right Riemann sum, you use the right value, and in the center Riemann sum, you use the center value. To do a Riemann sum, you simply sum the areas of all of the rectangles. You would multiply the width, which is the intervals of each small rectangle, and the height, which you can find using the value from the function. So for this Riemann sum, you would have 0 times x1, and then you add this value, which is f of x1, times x1. Then you have this value, f of x2, times x1. You do this so on and so forth over the entire interval of your integration to find the Riemann sum. Let's do an example problem. This is the curve y equals x squared. To begin, find the value of x squared on the left side of each of these small intervals. At 0, it's 0. At 1, it's 1. At 2, it's 4. And at 3, it's 9. At 4, it's 16. And at 5, it's 25. We're going to find the Riemann sum of this on the interval 1 to 5, and the width of each rectangle is going to be 1. So you find the area of each of the rectangles and you add them together. You have 0 times 1, 1 times 1, 4 times 1, 9 times 1, and 16 times 1. When you add these together, you get 30. The right Riemann sum is similar, except you use the right value for each interval. Add up the values of each of these rectangles and you get 1 times 1 plus 4 times 1 plus 9 times 1 plus 16 times 1 plus 25 times 1, which gives you 55. As you can see, Riemann sums aren't very accurate. They're just a way for us to approximate the area under a curve, and they help us visualize what happens when we integrate for exact value. In addition, in the left Riemann sum, we left out this much area. In the right Riemann sum, we overcounted by this much. The center Riemann sum uses the center values of each of these small intervals to determine the height of the rectangles. It gives us a much closer approximation. To do a center Riemann sum, simply find the value of the function at the center of each interval. The center of this interval is 0.5 because this goes from 0 to 1. So you get 0.25 here, 2.25, 6.25, 12.25, and 20.25. Do the same thing before and add up the areas of all of these rectangles. This gives you 41.25. If you integrate this function for its exact value from 0 to 5, you get 125 over 3, which is 41.666 repeating. As you can see, the center Riemann sum gets pretty close. It's less than 1. However, it's still not the exact value. As you can see, Riemann sums are kind of like Isaac Newton's hair. You can approximate it, but you'll never replicate it. You'll never find the exact value of the area under the curve.